the next person, rather than that if the order be maintained. Okay, why don't we get going? You've got 4 minutes. Good luck.
Today I will talk about separating red-blue points with an axis-oriented cross. We can see here we have this area blue, and this area red, this area red. We have a set of n points, some red, some blue. We need an efficient algorithm to compute a cross such that all the points in each quadrant is monochromatic. At least red and blue, they are separated. Current series of UPC presented an O(n)log(n) algorithm for red-blue wet separability. This one, they don't need the line X or Y orientated, so there is a matching set n(log(n) lower bound for this problem. My question is a special case of this problem. So the lower bound breaks down for the axis-oriented case. Now I will show you how to on the cross separate these points. First, we give every point x coordinate and y coordinate. So we set a line here. We move this line across the plane. So when we meet some points, we remember the y coordinate and the color. Then later on we can see this part have a minimum y coordinate, and this part have a maximum y coordinate. If they are separable, the minimum y of the blue color should bigger than maximum y of the red coordinate until when it meets some point like this. Then this minimum y is lower than the maximum of the red. Then we stop before reach this point, and this line we settle down should between this point and this point. Also, we got the minimum y and maximum y. This line should settle down between the minimum y and the maximum y. The rest of the work is keep moving this vertical line to see if the rest of the point still can separable. So all my work is to check every point to see finally it can separable or not. So this algorithm, I claim it only use O(n) times. So that's all I want to show. Maybe there have some specific areas. Maybe the point can sit on the axis, and maybe some other appear. Maybe blue, and red. They also can be calculated. That's all.
Okay, good. Okay, good. Give him a quick round of applause. Okay, next. Who's next on line? Okay, when you're finished, move the. Okay, next on line. Where did the? I think did you take the list of? Here we go. Sorry about that. So next on line. Next on line should be Clancy. If Clancy isn't here, keep moving. And next in line, somebody run up here. And if you don't run up here, the person closest should do it. Okay, so keep moving. You got to keep moving. We're going to do this fast enough. Okay, good. Thanks. Okay. This is your project.
Okay, so my project is a survey paper of extremographic theory. So my partner is Yang Liu because he's busy, so he hasn't come here. So it's only I to show the work. So first, let's know what's extremal graph theory. What's the problem of extremal graph theory? So because we have seen like simple Turing problem. So what's the maximum number of edges in graph with n vertices not in a single triangle? In fact, this problem is very simple. Also, sometimes we can meet this kind of problem, like at least how many edges are in graph of order n if it is forced to contain a path of length L. So let's see what's the same for these two questions. In fact, these two questions can be prescribed to forbidden subgraph problem. So if we are given a graph f, determine the maximum number of edges in graph of order n not containing f. So obviously we use ex nf to be denoted as this number.
No, you still got 3 minutes.
Okay. So for forbidden subgraph problem is
A lot of people weren't here. He was. This is the mic that you're talking to. What's on that screen is here, so you can read it off of this without having to turn around. Okay.
okay. So
relax.
Right,
Also, if you're using transparencies, try and put a piece of white paper in there.
okay, thank you. So forbidden subgraph problem always prime problems in extremal graph theory. Also, we need to know very special terminology of extremal graph. So what's extremal graph? In extremal problems,
Just wait.
okay, if a graph does not contain f, has ex and f edges, it is a extremal graph. So now we know what's extremal graph theory and what's extremal graph. So also according to standard format of forbidden subgraph problem, if we are given a graph f, the maximum number of edges in a graph of order n not containing f, so we know the problem can be divided to 3 different parts. The first is problems dealing with paths L and cycles C. Second problem is problem dealing with complete subscript KR. Also, sometimes we have some specific problems dealing with other special subgraphs like Hamilton paths and cycles. So we just follow this procedure to study to get some interesting and challenging results of extremal graph theory. So first, we read some paper and book about very simple problem of paths, about paths and cycles. So the result is very simple. For forbidden path problems, we got this answer. So because we have no time, just point it. That's the result we have. For forbidden cycle problem, also we have very simple result. Also we have give some specific proofs and talking about these two results. The most, I think, more interesting thing is about complete subgraphs. So first, the specific question is what's the maximum number of edges in graph order n without KR? So first, let's look at R-1 parted graph. Because we know R-1 parted graph is one kind of graphs suitable for this forbidden subgraph problems. But we don't know which kind of R-1 parted graph is extremal graph. So let's look at special R-1 parted graph, Turing graph, TR-1n. It's a unique graph. In fact, it's one kind of unique graph with maximum size in this kind of graphs. Also, we prove this kind of graph is just the extremal graph for forbidden complete subscript problems.
Sorry about that. Okay, thanks.
So review paper is so long time, so.
Okay, thanks a lot. Okay, let's now cut to a Demko. Okay, people at a Demko, can you can hear me, right?
Yes, I can.
Okay, so let me switch you on, and your cronies are going to be coming in a few minutes, right?
I believe they are.
Okay, good. Let's see if we can put you on here. And there you go. Look at that. That's pretty good. And let's put on the light here just for the sake of it. And you get going on what your talk is. Okay, good.
Professor, did you get the slides that I have?
Yes, I got the slides. Actually, I guess I could I have the slides, but the others won't have it, but that's okay. Why don't you go?
Okay. What I was going to be studying is a little twist on Fibonacci numbers. The Fibonacci numbers, as we all know, is defined by f of n is f of n minus 1 plus f of n minus 2. That can also be written as the summation as I goes from 1 to 2 of f of n minus I. And if we look at it in that way, we can see that that can be further generalized to allow the upper bound of the range of I to be variable. In some sense, we can look at it as f of kn is equal to the summation as I goes from 1 to k of f of n minus I. And for lack of a better term, I have labeled these the K-Nachi numbers as a general term. And as such, there are actually two possibilities for the definition of this type of sequence that I had seen. Obviously, there's even more than that. But the two logical ones that I had come up with were, in the first case, predefining the first k terms. And what I've done there is f of k0 is equal to 0, and f of kn is equal to 1 for all n between 1 and k, and f of kn for all n greater than k is equal to the summation for I going from 1 to k of f of n minus I. And in that sequence, for example, with a k equals 3, you get a series of 0, 1, 1, 1, 3, 5, 9, 17, 31, etc. And a second way of defining this sequence is to assume 0 for all the negative values of n and start the general summation at n equals 2. And in that case, we have f of k0 is 0, f of k1 is 1, and f of kn is equal to the summation for I going from 1 to k of f of n minus I times the Iversonian term of n minus I greater than or equal to 0, and that's for all n greater than or equal to 2. And in this case, with a k equal 3 example, the series looks like a 0, 1, 1, 2, 4, 7, 13, etc. Now, obviously, only one of these two will be a better fit for what the Fibonacci's pan out to be. And to figure out which one, what I've done is I've taken a look at one of the natural or physical world examples of the Fibonacci numbers, which is the number of ways to climb stairs taking at most 2 steps at a time, which is equivalent to Fibonacci of n minus 1. So what I've looked at is which of the above sequence definitions represents the number of ways to climb n stairs using at most k steps at a time. Should I continue, Professor?
No, I think that that's right all we can do. So let's say thanks.
Okay.
Are any of your cronies there?
Yes, they are.
Okay, get the next one up. We'll do the Ademco people are next. Let's get the next ones up.
Okay.
Where the slides
All right. My name is Damien Tellini, and I did something similar to Fibonacci as Jim Kern did. What I wanted to do was see if the sum of the inverted Fibonacci sequences would converge. I was trying to do that analytically, but I had a computer, and it was easy for me to use a software program like Excel to see if that converged. And basically, the number converged to 3.35987. Now, I have yet to determine what's the significance of that number, but it does converge because there was like 20 consecutive numbers that it didn't change. Well, I was in the mood for doing sums, I said, well, let me try to take partial sums of the Fibonacci numbers and see what I get. And basically, I was forming the sum of from I equals from I from 1 to n of f of n of the Fibonacci numbers, and I would make columns. And these would be the partial sums once, twice, 3 times. And what I would get is a table. And the first column is the Fibonacci series. The second column, which I call S of n, is numbers 1, 2, 4, 7, 12. And basically, those numbers are, since the first 2 Fibonacci numbers are 1 plus 1 gives you 2, then 1 plus 1 plus 2 gives you 4, and so forth down the line. That would be the first partial sum. And I continue that, and what I did was in the next column, now you can't see that here, I kept doing the sums of the previous sums. And what I noticed in this in the columns were the ratio. Now I noticed that as n goes to infinity, the ratio of S of n to the Fibonacci n's were all the same for each column, and that came out to 2.618. And that has some significance because 2.618 is 5 plus 1, which is also equal to 5 squared. So it seems like when I wrote these columns, for instance, the that 5 came, was included in there. And then also what I noticed is we all know that the ratio of f of n to n f of n minus 1 is phi, which is 1.618. When I went through all the other columns, all the other partial sums, like the limit of S of n divided by Sn minus 1, and the next column was R of n divided by Rn minus 1, those also had the same ratio of phi, which was 1.618. That kind of amazed me. It would be nice if I had the table to show you on the screen, but I guess when I submit you'll see. Also I noticed is to generate the Fibonacci numbers, what happened when I looked at the two columns, I noticed that to get the Fibonacci f of n, all I would need to do is go to the next column. Oh, that's it?
That's it, I'm afraid.
I guess that's it?
Sorry about it. Thanks a lot. Okay.
Okay.
Sorry about it. Is the next one there? Is Eugene there?
Yep.
Okay, sorry about that.
That's okay. Do I have slides available, or I don't have anything?
I have the slides. I have your slides. I have your slides, so you can just give it, assuming we have the slides. If you have a projector there, that's good, but you don't have a projector there, right?
We don't have a projector set up here, so.
Okay, I have your slides. We'll assume that. Okay, thanks.
Okay.
Sorry about that.
My purpose was to find out, to estimate the correct answers for a number of students answering a number of questions of various complexity during a number of exams. And since the problem is pretty vaguely defined that way, my first task was to formalize the task and to provide math description for it. So I assume that there is a 3-dimensional array that contains all the data in there. And I introduced a category, which is a parameter which I call complexity. And complexity is defined in reference to the student level. And the complexity changes from 0 to 1. I assume that depending on the student level, the probability of the correct answer falls exponentially and reaches a floor level which is 1 over k, where k is the number of possible answers. That basically means that the answer becomes random. We have to make a number of assumptions. The first assumption is about the complexity distribution, and the other about the student level distribution. If the student of level is uniform, in other words, if all the students have the same level of knowledge, then the majority voting will suffice, and the best estimator will be a majority over all the students, and we don't really need a third dimension introduced by a number of exams in there. However, my third slide indicates that if we have a number of students who have a different level, we don't really have a statistically significant number, and that is when the number of exams, the third dimension, comes into play. So the best way, the best strategy, in case we have students of different level, is to evaluate the students first and to come up with a student who is the most knowledgeable, and then rely on his answers. And the estimator suggested was the relative number of the correct answers over the students over throughout the exams. My table indicates on a sheet what that is. If we assume that the original assumption about exponential shape of the answer probability is correct, then by taking logarithms and taking the ratio, we're able to evaluate the ratio of their levels, of student levels. Then, as we have a number of students level, we can come up with the least square line, which would allow us to find the level for each student and pick the best one, to choose him as a final indicator.
Okay, thanks. Very good. Okay, thanks a lot. Okay, thanks. Okay, look for it. So that takes care of the three of you, right? Thanks a lot. Okay, good. Let's take a look at that. Sorry. Okay, let's not go back to from VHS. Let's go back to. Is this right? Okay. Now let's get back to locally again. We've had several people. We're now back up here. Clancy. Okay. Keep moving. Okay, keep moving. See where you are next. I want to see fast movement from one to the other. Okay. So get to the front row if you're next on line. Okay. Last one to go. Put your thing up here so that we can sort of get a flow. Keep going.
Okay, my name is Tom Clancy. This is my presentation, sort of mid-course, long before completion. My area of interest was graph theory, and this is the nature of my problem here. Does every graph of minimum degree greater than or equal to 3 have a cycle length of 4, 8, 16, 32, etc. for some power of 2? And initially thinking about this, if you think about a series of intersections on a grid, like Manhattan or something, a two-way or a four-way intersection rather would have a degree of 4. But if you kind of bend it and you think about the sides and the edges, every intersection has a degree of 3. And it would seem that if you have a certain amount of intersections that all have that many streets that come in and out of them, then at a certain point you might be able to make a guess and project how many intersections you could possibly travel through, or a path length, the cycle length, to get back to where you started from. So that's where I began. If you consider a graph with a min degree of 2, for example, the simple triangle, you've got one street that comes in and one street that goes out. And our cycle length for that particular case is 3. But by adding 1 degree, each one of those intersections has to have another road coming in or going out or whatever. And that one extra vertex, that one extra point, even if it's a single point or a single vertex that we add, we're going to have a cycle of length 4. So it seemed like this is starting to go somewhere. And of course, this ugly thing redrawn looks like a like that. Okay, and as you look at this, it seems like it grows with some sort of regularity. But how? I'm not sure yet. Got about a week, I think, or less. Okay, I thought this was a curious design. This is sort of a regular, some sort of a regular shape that has a growth. and you could extend these down, and it sort of begins and then picks up again where it ends. Not sure. I think that's got something to do with it. That growth of 3. I really think that it's important to stick with the 3 case, because you can add as many lines as you want and get something that's not going to help you with your conclusion at all, for example. I think I'm at my 4 minutes, but that's all I have to say.
Thanks a lot. Very good. Next. Okay, who's next? Got to keep moving. Got to keep moving. Okay, who's next? Okay. Again, we want anybody, the person who's next in line sitting in that seat to get ready for a quick spurt up to the blackboard. Okay. If you don't know when you are, sit in that seat anyway, so I can get you next. Okay, go.
Okay, my topic is the geometric construction. The problem is if you were given some kind of shape and openings, whether we can make sure that one shape can only navigate through only one opening. Right. For example, in this graph, we are giving some shapes, for example, a square, a circle, and a triangle. And we're having a kind of board, and we have cut out some openings. So we'll try to put the shapes whether it can pass through the openings, right? And so, for example, in this one, it seems that the triangle can only pass through the triangle, but the circle cannot pass through this one. And in this one, we're not allowed any deformation of the shape, and only translation and rotation within the plane. So, in my project, only majorly consider 2 problems. The first one, whether can one design such a toy to make to satisfy this requirement, and the second one is that if you were given some set, how to find the large subset that satisfies the requirement. First, let's see some observations. What does it mean when shape can navigate through openings? That is, at a certain position or orientation, the shape S, the outer point of shape S will fall into in the boundary of O. That is, it is completely enclosed in shape O, so that means can pass through. So we have some naive idea is that if we make such a constraint that the area of the shape is the exact same as the opening, so then we can make a conclusion. Any shape can only navigate an opening if and only if they are identical, and if they are of the same shape. For example, in this one, I use red line to draw a shape, and the blue one is the opening. So, if the two are of the same area, and if they are not of the same shape, so then the blue one should have some part be outside of the boundary, so the B cannot pass through A, as and vice versa. From this observation, we come up to a design principle. That's including 2 parts. First, we require that all shapes and all openings have the same area. And the second one is no shape and opening should be identical. For example, we can use circle, triangle, rectangle, polygon, and make sure for each category the shapes won't have the same parameters sets.
Thanks a lot. Okay, thanks. Okay. Next. Yeah, take it. Sorry. Come here. Sorry. Sorry, wait here.
Hi, my name is Kanchan Bhargav, and how do I adjust the slide, Professor?
That's fine. Just speak louder.
Okay. The topic of my project is algorithms for coloring 3-sectored hexagonal cells with 3 colors. Now, what does that mean? Before I move on to that, let me tell you the application of this project. We've seen cellular phones, and perhaps some of us have even used cellular phones. Whenever we design a cellular network, the whole area to be covered is divided into hexagonal cells, and each cell might further be divided into sectors. Now, the aim of this project, and and when we have a cellular network, we are supposed to use certain frequencies for the operation of the cellular phones. So in a hexagonal network which has been divided into 120-degree sectors, the problem of my project is that if I'm given 3 frequencies, or say 3 colors, red, green and blue, then if I place one color in each sector and I have a layout of n hexagonal cells, then how to color a whole grid of n hexagonal cells in a cellular network such that the following constraint is met. And what is the constraint? The constraint can be explained with this diagram over here. Say suppose this is a hexagonal cell in a cellular network and these are the 3 sectors. When I use 3 frequencies or 3 colors to fill up all these cells, the coloring should be such that blue, green and red are adjacent to each other, but no red or red are adjacent. Say I don't have red and red over here, or I don't have green and green over here, or say blue and blue over here. No 2 same colors should be adjacent in any of the 2, should be there in any of the 2 adjacent sectors. So that is the aim of my project. Now I have 2 options. I can color a cell either red, green or blue, or I can color a cell like red, blue or green. So the 2 cycles that I have are red, blue, green, which I term as 1, and the second is red, green or blue, which I term as 2. Coming back to this slide, the aim has been specified. The constraint, as I said, no 2 adjacent sectors should have the same color. Now what is the method? As I said, there are 2 cycles, red, green and blue, or red, blue and green. So the method or the approach that I have is start with any one hexagonal cell surrounded by its 6 neighbors. This is one hexagonal cell surrounded by its 6 neighbors. I randomly place scheme 1, which is red, blue, green, or scheme 2, which is red, green, blue, in this whole set of one big polygon. And then the next step is fill up this larger hexagon or polygon, with red, green, blue or red, blue, green, such that there are no conflicts. The conflicts being 2 adjacent sectors having the same color. Try to replicate the pattern horizontally and vertically. That means if I have this pattern or any pattern with 1s and 2s in it, how many times can I replicate it horizontally and vertically so that I fill up the whole grid of n cells, n hexagonal cells? Then figure out if any special restrictions apply for a given combination and a way to get around this problem. Say suppose if I have this pattern replicated over here and then again on top of it I have the same pattern. It might be so that there is a red over here and another adjacent red over here. So that means I can't directly juxtapose this pattern with a similar one of this kind. So that is the restraint. And okay, just one line. Okay, and the result, I'm still working on that. So the result is that some similar patterns might occur in a particular n hexagonal grid, and that's what I'm trying to figure out. Any algorithm which gives the best way to figure out how to fill up n hexagonal cells.
Okay, thanks a lot. Next, let's see.
My name is Kathy. My partner is Daijun Yu. We are working on an implementation of an algorithm. The algorithm we're going to implement is the optimal Chinese postman's tool algorithm. So what is the Chinese postman's tool? Chinese postman's tool is to find a minimum path that visits each edge in the graph at least once. So let's look at a special case. A special case is an Alerian graph. An Alerian graph is a graph that we can traverse each edge in the graph exactly once. So if the graph is Alerian, it means we can the Alerian cycle will be the optimal Chinese postman's tool of that graph. But generally, graph will not be Alerian. So our approach is to make the original graph into an Alerian graph first, and then exercise a way of finding an Alerian cycle in the graph. So how do we make the graph into an Alerian graph, an ordinary graph into an Alerian graph? So the first thing we do, because an Alerian graph has all the vertices with even degrees. So to make a graph Alerian, we have to connect those all degree vertices and to such a way that pairs such a way that we can make all the nodes into all even degrees. So this problem becomes a problem of finding minimum matching between all the odd degree vertices. So how do we find this minimum matching among the odd degree vertices? So first step, we need to find the shortest path of all the odd degree node vertices to the other odd degree vertices. So this we can use the Castro's algorithm of dynamic programming to do that. And second step is how do we find the minimum matching once we have all the shortest passes between all the odd degree vertices. We can find a lot of implementation available on for distribution of maximum matching implementation, but we didn't find anything about minimum matching. So the way we convert a minimum matching a maximum matching algorithm into a minimum matching algorithm works like this. Let's see, we have a graph like this, and the first step is we convert each weight in the graph into by subtracting it from a large number, and we get a new weight that assigned to the new graph. So the weight WO corresponding to WO prime in the new graph, and we exercise a maximum matching on the new graph to get the maximum matching, and that will be a minimum matching of the original graph. So once we have a Alerian cycle, then we can do find an Alerian cycle on the revised graph, and the problem of Chinese postman's tool is solved.
Good, thanks.
Right.
Okay.
Thank you.
Okay, next. Lee. Yeah, go next.
Professor,
Yes.
we're gonna disconnect from the class at this point.
That's acceptable. That's acceptable. Okay, go. See you.
Thank you.
All right, thanks. Okay, go.
My name is Xiaojun Liang. My topic is improved ray tracing algorithm for computer graphics. First, the introduction. Ray tracing algorithm is a traditional algorithm. We have a viewpoint here, and we have a view screen, and this is the representation of 3D objects. Here is the triangles. From the viewpoint, we have many rays, which will intersect with these 3D objects. The problem is that there are many pixels in the view screen. The number is very large, and at the same time, the number for the triangles is also very large. So the speed for ray tracing is very slow. Second one, improved algorithm. My idea is that we project each triangle into the view screen, and for every box in the view screen, we remember the possible triangles, and during the intersection process, we just intersect with the possible triangles. Okay. This is my model. Here, XYZ is a triangle, which is projected into the view screen. And here, we index these boxes 1 to 16. And x here is 7, and y is 11, z is 13. We define 4 random variables here. M sub max m is the max number of x mod n, y mod n, and z mod m. So, m sub max minus m sub minimal plus 1 times m sub max minus m sub minimal plus 1 is the average number of triangles to be intersected for every segment. Then we assume that each triangle is small enough, so we can have this one. M sub max minus M sub minimal is less than M divided by 2. Okay. So this one, the conditional expectation, means the average number of triangles for every box. To solve this conditional expectation, we use Schwarz equation, which is here. This one. First, we calculate the conditional probability of this random. I don't want to discuss it in detail here. So the following results is something like this. Here, if n is enough, we can get good results. It's 0.11 n. Here, n is the of all the triangles, so the improved speed is dramatically higher. Okay.
Next. Okay, Ping Li. Next. But if not, someone get into the second work. What? Okay, go. What? Go.
Okay. Hi, my name is Ping. Originally, I prepared for 4 pages, 1 per minute, but thanks to Tom here, I can get rid of the first page, so I have 1 less minute to nervous about. I'm also working on the hypothesis that every graph with each vertex having a degree of equal or more than 3 must have a cycle of length 4 or 8 or 16 and so on. But I took a different approach trying to show this is true. Okay, here's what I've drawn for such a graph that doesn't have a cycle of 4. Well, how can you tell it doesn't have a cycle of 4? Well, I break it down into basic units of cycles that it's either a cycle of 3 or it's a cycle of 5. Now, obviously, in lengthening the cycle of 5, you can get cycle of 4. And no cycle of 3 touched by an edge. So the best, so is it obvious that this doesn't have a cycle of 4? Where?
The side edges and the
Okay.
No, that's a
Oh yes, it has a cycle of 8. Okay. So basically, the method method I'm using to check if it has any cycles is that I break it down into units of smallest cycle possible, and make sure that those cycles doesn't have any cycles that I don't want, then I use the fact that the length of cycle A plus the length of cycle B minus the shared edge, like in here, we have a cycle of 3 and a cycle of 3. Oops. We'll have 2 cycles of 3s, and they share one edge here. So the cycle of this whole this combined composite cycle is 3 plus 3 minus 2 times 1, which is a 4. So, and here's my attempt at finding one that doesn't have a 8 cycle. Kind of pretty. Why is this so complicated? Okay. This is the things I'm trying to avoid here. I try to avoid 2 cycle 5s sharing one edge. 5 plus 5 minus 2 times 1, which is 8. I try to avoid 5 with sharing 3 edges with 3 cycles. That will give me an 8. And 5 sharing 1 point with 3. So basically what worked for 4 doesn't work for 8 anymore. So I have to put in 6 to separate 5 and 3s so they don't come up, so that no cycle of 8 come up in this case. Okay, so my point being that comparing the complexity of the 2 graphs, you can see that if you want a graph that doesn't contain 4 or 8 or cycle of 16, I don't think I can find it, but it's going to be very complex. And for me, I experienced that complexity personally. The first one, it took me 10 minutes. This one took me 5 hours.
And the talk took you 4 minutes. Okay, thank you. Very good. Okay, who's next? Next one is Jun Wang. Right here. Okay. Next one, Zhao Ming Pan. Okay, get moving. Okay, the one after you is Yuk Tian. So you get up in the warm-up seat. Okay, thanks.
Actually, it's really nervous. So.
Okay, don't be nervous. Go.
What I really want to do right now, actually, I want to go home. So my talk is about the automatic proof of the hypergeometric identity. So at first, let me show you what's hypergeometric. Serious. What's this one? So like this one, in which the T0 is equal when the ratio of 2 consecutive terms is the ratio function of the summation index k. So like if the T, okay, let's
hit the one that says light.
This one?
And then forget it for a few minutes. Okay, go.
Okay. So
and that's what they're saying up there, okay?
Okay.
And there's a zoom there. You can widen or telephoto if you want to make it tighter or looser. And you're going to talk into this mic. And if people would just be aware of the cameras being on when you're walking in and out because you're walking in front of your presenters.
Okay, don't worry too much about it. Go
okay, so the hypergeometric series is like this one. And where P and Q are polynomials in K, so Tk is called hypergeometric term. So example like these two, which we saw in many in the class. And there are basically 3 methods to do the proof of hypergeometric identities. First one is the combinatory, and the second is the generating functions. Actually, we learned in this class. And the third one is automatic proofs. This is I'm talking about. So the principle of the automatic proof is that we want to prove this one. This identity, first we find a recurrency relation satisfied by the sum of the left side, the f in k. And the next step is show that the f in satisfies the right side, f in satisfies the so the same recurrency by the substitution, and the last one checks that enough corresponding initial values of both sides are equal to each other. So on this basis, powerful high-level computer algebra programs for personal computer and workstations will develop to prove and discover many kinds of identity. So there's 4 main programs, algebra programs, map, and so forth. So the computerized proofs of identity date back to 1945 when Alerian did her PhD thesis at the University of Michigan, and she developed a method for finding the recurrence relation for hypergeometric polymers derived from the series expansion of the polymers. So her general algorithm is that when the if in K is a double hypergeometric, it means that these two equations are right. Then we need to find a recurrency for the f and k of the form like this one. And the steps to find the recurrency are, first we try the smaller I and j. For example, if I and j is equal 1, and divide each term of this equation by f and k, and reduce each ratio of every item of this one. The last two was that it means that why I talk at the first that it means that if you cannot prove the identity, it doesn't mean that you are not smart. And the second that if you have any problem, you can switch to the automatic proof.
Next, okay. Next, let me adjust the zoom. Hold on. Let me try to get a couple things. First of all, let's get lights, so we get more lights here. Zoom. Let's try. You want it less zoomed, right?
Yeah. It's not clear.
Is that okay? That's good enough. Okay, don't worry about it. That's fine. Go.
Okay, that's my question, number 19. The question is counting multi-term functions. It means how many Boolean multi-term functions or how many ways to order the n 2 to the n subset of n elements by Thomas. It's not clear, right? That is, how many ways to align the 2 to n subset of the element so that any of the subset only appear on its left side. Still not clear, right? This is one example. Suppose we have 3 elements, 1, 2, 3, and we will get 8 subset of this one, right? And one alignment which meets the requirement is this one. For example, any subset of the subset will appear on the left side. Suppose for this one, 1, 3, the subset 1, 3, and the empty will be on the left side. And also for all the other case. For this one, this alignment doesn't meet the requirement because you see the subset of 1, 2 is on the right side. So, and also subset of 1, 3, 3 is also on the right side. So that's this one is not good. So the problem is how many alignments we can get to meet this requirement. There is a lower level bound and there is lower bound and the upper bound. Here I just talk about the lower bound. The algorithm I can use is the topological sort algorithm. In the topological sort, we can draw the subset like this. You can see the relationship by the subset relationship. Here I use the depth first sort algorithm. Suppose we want to start from here. We record the time, start time 0, and we have 4 choices, right? Suppose we choose this one, and then we have 3 choices, and then we go here, and then we visit here, and then we visit here. Until here, we have no way to go. So we finish this one, and then record here, 1, 2, 3, 4. That's the last one. Then we go back, 1, 2, 3. This one has been visited, so we have no way to go. So we go back here. So we record this one and go back, 1, 3. For 1, 3, we have 1, 2, 3, which hasn't been visited. So we go here,
and we visit this one. Again, when we reach here, we have no way to go. So we finish this one and record here, 1, 2, 3, and then come back. And so 1, 3 has been finished. And then go back, is 1. Then for the 1, we have 1, 2, and 1, 3. 1, 4 hasn't been visited. Suppose we pick up 1, which is 1, 2, and we go here. For the 1, 2, this one can go here. So first visit this one. So this is so-called depth first. It means visit all the child until visit this node until all its child has been visited. So we go here and with this one, we record 1, 2, 4 here. After that, we go here. All the child has been visited. So we finish this node. We record 1, 2 here. And when we go back 1, and the 1 have 1 child, which is 1, 4, hasn't been visited. So we go here, and all the child of this one has been visited. You see here. And so we record 1, 4. And again, we go back to 1. Until now, we visit all the child of 1, so we can finish with 1. So this is called depth first sort algorithm. This algorithm gives you a method to get alignment of the thing, which is correct, which meets the requirement. But it doesn't give you how many alignments you have. So that's how, this is standard, in fact. That's how my work. The choice of upward weight, I figured out, is this one. So for the first choice, you have n, and then n minus 1, and so you have n, this one. And the choice for the downward weight means you come back, you get here, you still have some choice. Suppose you get 1, you still have some choice. It turns out to be this one. So that's a first round. And for the second round, after finish 1, the left thing is exactly the same, except, okay. Anyway, the conclusion is this. I hope it's right.
Okay, thank you. Okay, let's see. Luke Tian. Okay. One. Just take a look at this thing here. Some people's signatures. Where did the roster go? Okay, here's my roster. Some other people may be on here also. Let's see. Zoom it in. Yuk Tian, is he or she here? That was you? Wait. That is you. So then I may have missed one. So who was Zhao Ming Pan? That was you. Okay, so okay, 17. Okay, so everybody here I think I've gotten. I'm sorry about that. You did not go yet. Well, you go now then. Okay, and who's next? Okay. Who's next after this? Does anyone recognize their signature? Okay. Okay. Whoever you are, get next. The one after you, Jiang Yin, Hu Bing Chen, Chi Ki, Tatjana Vitrich, and Sylvia Paquette. So you guys know the order. Let's go. Slightly smaller. Go.
Okay, the problem I'm working for is number 20. It's a partitioning strategy for weighted coupon collector approximation. This problem is based on a paper which by Shiyong Lu and Professor Steven. The basic idea is this. Okay, how can you calculate the away if you want to, let's say, you want to collect the coins from the 1957 to 1997? Then how do you know how many? What's the number of years? What's the number of coins you're supposed to get before you can get a whole set of these coins? So how to deal with this? First of all, the number. It depends. Of course, it depends on the how is the probability? If you pick up one coin, how is the probability it will be fall into one specific year? It depends on three factors. Okay, just to be simple, the three factors are the mintage of that year, the collector pressure, and the age of the coin. So you can get a graph here. It's the mintage and the probability here. So if the probability is the same, it means that if you got the same probability for each coin, it's easy to calculate. The formula is given here. But in this example here, it is much difficult because the probability for each coin is much different. Generally, we have a formula here to calculate it, but this formula is not practical in reality because say here, if you want to get the 1957 to 1997, it's need the calculation power increase exponentially. So the problem is here to get the up bound and the lower bound of this estimation of this coin collector problem. There are its method here given in the paper to get the lower bound and the upper bound. The lower bound, the idea is if I wanted to get the collector from 1957 to 1997, it's too large. This number is too large. We can calculate for a smaller number. If the m is a year, if it's equal to 20, then it's easy to calculate. But now the number of years is 40, so it's no way to calculate it. The way to get the lower bound is to, okay, let's say, if I want to collect each year from 1957 to 1977, then I add all the probability of the from 1978 to 1997. I divide it in 20 groups by this way. Then the idea is if I get the site from 1957 to 1977, it's very possible that I have the site of the, okay. Okay, thanks. Okay, I didn't get into the problem yet, but okay.
Okay, well, I'll see you read it number 4. Okay, thank you.